So let's learn about what we can learn from bones today. So that's forensic anthropology. So we've talked about pathology, which you're looking at the soft, meaty stuff, and a little bit of work with bones. So mainly you're dealing with the soft, meaty muscles and the brain and the heart, all your organs, tissues, that sort of stuff. Now we're going to be dealing with bones. Why is this thing? Times when somebody is murdered, or even if, say, someone who dies and their body's left for a long time, but the only thing you find are bones. So they can reveal a lot of secrets, including possible identities. So let's talk a little bit about your skeleton and what it basically does for you. It gives you a framework for support. Without it, you're not standing up. All those muscles do nothing. They protect those soft organs of yours, your heart, your liver, your kidneys. They move the body, so your bones and your muscles act as levers so you can walk and lift things. They help store calcium. They help form new blood cells in the red bone marrow. And they store fat in the yellow bone marrow. So a lot more than you're expecting for those poor bones. How many do you have? You got 206 in a human. 80 in the axial skeleton. That's 28 in the skull, 24 in the ribs, and 26 in the backbone, and 126 in the appendicular skeleton. So you're looking at your legs and your arms there. So the making of bones is called osteogenesis. You can see the Genesis from the Bible, the making of the world. So osteo, bone, making of bones, or ossification is another term for it. So your bones actually begin to form around the 8th week of pregnancy, and basically it continues until adulthood. Your osteoblasts, they're your bone-forming cells. Your osteocytes are your mature bone cells, and osteoclasts, those are the ones that break down and reabsorb bone. All right, we got a couple other terms here. These are less important for us. You get intramembranous ossification, endochondral ossification. So this is basically when your cartilage gets replaced, or when your connective tissue gets replaced. And I guess they are kind of important because you can take a look and see when this occurs in the body, and you can get an idea of an age of an individual. Because if certain things have finished, like endochondral ossification, you know that the skeleton has to be over in age past the 20s. Here's an x-ray of a newborn baby. And you'll see some gaps there. Look at those gaps. Aww. And those gaps between the bones indicate cartilage. So bone continues to form and change into adulthood. Bones get thicker in response to weight and muscle activity. That's one of the things they always tell you as you get older, like me, woman in my 50s. They always say you got to watch out now because you can start to have bone loss. In fact, one of my friends had thyroid cancer in her 20s, and she had to have her thyroid gland actually killed out. And she's been on thyroid medication for years now. And one of the side effects of thyroid medication is bone loss. And she just found out that she's going to have to go on a bunch of drugs now because of the massive bone loss that she's had. So they tell us that as we get older, we need to start doing weight-bearing exercises. In fact, stuff like walking, which is actually a weight-bearing exercise, or lifting light weights. It doesn't have to be, 50-pound weights. It can be little 5 or 10-pound weights. Actually helps your bones stay strong, which, like I said, especially if you're a woman and you get into your 50s and 60s, this is very important. You don't want to be breaking things as you get older. All right, so let's sort some bones here. You got your long bones. They're longer than wide. They tend to have bulky ends. With these guys, you can extract height and general frame size. These things are like the femur, the tibia, the fibula, the humerus, the radius, and the ulna. So you can actually measure these, do a little bit of math, and get a general idea of the height of somebody. And whether or not, they were big and bulky or petite. Short bones, these tend to be cube-shaped, wider than they are long, mainly spongy. These are your tarsals, carpals, your wrist and ankle bones, so your fingers, basically your toes. And guys, remember, you can stop this anytime you need to take notes. I'm just going through it, so feel free. You got your flat bones. These tend to be thin, flat, curved. So think of your scapula, your skull plates, your ilium, your ischium. And then you got your odd ones here, they call it irregulars. They don't fit in any place. They tend to be mainly spongy, with a thin layer of compact bone. Things like your sternum, your sacrum, your vertebrae. All right, I would not ask you to do this, but one of the quick ways you can determine if something is bone is to lick it. Bone is porous and rock is not, so bone will stick to your tongue. Very disgusting. Is it human? Because remember, a lot of bones that you find aren't necessarily human. I remember reading that this one forensic anthropologist working with 9/11 got some bones in, and they weren't human. They ended up being something from a slaughterhouse that was nearby, and they thought it was human. So, and some of these bones, when they come in, you can't always tell initially. So what you got to look at is the size. Is it a chicken leg or a human finger? A bear foot or a human foot? Pig ribs or human ribs? And a lot of these, unless you have the context of the entire skeleton, look kind of the same. So how do you tell? You compare it to known bones or try to fit the bones to a human skeleton. So with some of your long bones, there, you look at the ends of them, and the angle will indicate the posture of the animal. Remember, we're an animal too, and it will be different in humans since we walk upright. You can look at the diameter of the bone when examining a cross-section. When you look at a human, the cortex of a human is approximately 1/4 of the thickness. And the cortex of large mammals, when you look at, horses, cows, bears, is 1/3 of the thickness. If you look inside the bones, something called the osteons, they're randomly distributed in humans. In non-humans, they are rows like bricks. So if you want to figure out how large this person was, you're going to use the long bones, the humerus or the femur. So if you want to figure out approximate height, you take 2.11 times the femur length plus 70.35. The size of the bones can actually give you a dominant hand. If you look at it, a dominant hand is going to require more muscle, and you can actually look at the bone where the muscle attaches and get an idea of dominance there. And you think about that, if you're dealing with somebody who's killing somebody, generally if they're going to be wielding a weapon they're going to be wielding it with their dominant hand. I don't know about you, but I am right-handed and I can do some stuff with my left hand, no doubt. But comfort-wise, if I was going to, handle a knife or a mallet of some sort, I'm not going to be swiping somebody with my left hand because I'm probably going to miss, or it's going to be kind of wussy. I'm not going to get done what I need to get done. You can also get an idea of the age of the person. And there's some things that can actually be a little sneaky here. So if the person was very active, the bones are going to look younger because of, you're doing a lot of this activity on them. And they're going to have more mass to them. They're going to be stronger. So they're going to appear younger. You can have someone in a country that is very poor and they're not getting good nutrition, and there's a lot of starvation issues, or the food isn't good, and the bones can appear older because they're not getting what it's needed. Disease, like arthritis or gout, health issues, stress. You can take a look at someone who is working, say, in building homes, and they're wielding a hammer over and over and over again, or they're doing a lot of physical work, and that does take a wear and tear on your bones. And there's osteoporosis. My friend has it. She is 1 year younger than me. She's 52. And she has a good case of it, and she's having to go on medication for it. Here's some information about what happens with the long bones and age. Oh, my computer's doing fun things again today. Sorry about that, guys.